Hi, good morning. We are going to learn our new parent graph. So welcome to Unit 2, Section 3, Graphing. So first, we need to actually graph our parent graph. So we are looking at a new version, y equals absolute value of x. Now, as always, you have a lot of tools to graph. You can use a graphing calculator, you can use a website like Desmos. Any option is pretty much okay. But let's say you don't have any of that, and we're going to graph it by hand. Our standard start then would be to make a basic XY table and see what we get when we plug things in. So if I start with kind of our standard -2, -1, 0, 1, and 2, I can actually plug those in. So absolute value of -2 is just 2, absolute value of -1 is 1, and so on. So this gives us our basic points for our absolute value graph. I can go ahead and plot these points that we have and see what this basic graph is going to look like. So -2, 2, -1, 1, 0, 0. Notice we're getting a perfectly straight line here. 1, 1, and 2, 2. So this is actually going to be our basic graph. If we were to continue out, we'd end up at 3, 3, 4, 4, -3, 3, -4, 4, and we get this very clean V shape. Comes to a nice firm point right there at the origin. So this is our new parent graph, y equals absolute value of x. If we go look at this, we can see certain characteristics. For one, goes left forever, goes right forever. So our domain is, once more, all real numbers. Our range, as we come up, we're starting at 0, and then it goes up forever. So our range is 0 to infinity. Our x-intercept, well, we're touching the x-axis right here at 0, 0. So that's 0, 0. Our y-intercept is also touching the y-axis right there at 0, 0. And we have no asymptotes. So this is our basic parent graph. Now I'm going to kind of review some of the changes we can do, and then we'll look at the overall formula for these graphs so we can see how things happen. Now when we take a graph like this, there are several changes that we can make. So the first one is that we can actually add something to the end. I'm just going to use k as a place marker. So if we add a number to the end, it's actually going to change our graph. Let's say we wanted to graph that y equals the absolute value of x plus 2. Well, if I were to go through and plot all those points again, we'd see something very specific. So if I make my XY table, and I use those same basic points, y equals absolute value of x plus 2 would become 4, 3, 2, 2, 3. Wait, assuming I can actually add 3, 4. Three and 4. So now when we plot it, we can see that each point has simply been moved up 2 on our graph. Otherwise, the graph is still the same shape. So we're at 0, 2, and then we get that same distinct V shape. But the whole thing's simply been moved up. So this is called a vertical shift. Any kind of number we add or subtract at the very end moves the whole graph up and down. Well, let's look at another example. What if we simply move it another way? So how about y equals the absolute value of x minus 4? In this case, were we to go through and plot all those points, we'd see that the entire graph has actually been shifted left or right when we add something inside of the absolute value. So instead of being centered at 0, 0, this graph has been shifted. And when we actually plot it, we find it's the opposite. So it's been shifted positive 4. So it's 4 units to the right. So our 0, 0 would be starting right here, and we'd still get that distinct V shape coming up as we go. Finally, we could actually change any number in the front. So if I did like 2 times the absolute value of x, well, that's not moved up and down, and it's not moved left and right. It's actually going to make the graph skinnier or fatter. It basically accelerates or slows down how fast it climbs. So if I'm multiplying it by 2, it's going to go up much faster. So we're still starting at 0, 0, but instead of 1, 1, we'd make it all the way to 1, 2 already. 2, we can make it all the way to 4. So our V is still the V-shaped, but we've actually increased the rate at which we climb. So our general formula for these is y equals a times the absolute value of x minus h plus k. This is our general formula for graphing an absolute value. And each of these numbers means something particular. So h is the horizontal shift. It's how far we moved left or right. Notice that it's minus in the formula. So when we go to look at it, it's actually going to turn out to be the opposite value that we see in the equation. K is the vertical shift. That's how far we moved up and down. The sign of A tells us orientation. Are we going upwards or are we going downwards? So a positive A, we go up. A negative A, we can actually come down. The size of A tells us if we're making it fatter or skinnier. In particular, if we look at that A value and it's greater than 1, then that says that we're going to go up faster. So the graph gets skinnier. If that value is less than 1, so if we end up with some fraction, say like a half or a third or something else, that's actually going to make it go slower, or the whole graph will end up fatter. So these are our basic ways of just looking at a formula and knowing what's happened to it. So we can use this to compare it back to the parent graph. So as an example, if we had something like y equals 2 times the absolute value of x plus 3 minus 4, then I can actually graph this or sketch it at least without really needing to use any equipment. This is an absolute value graph, so it's going to look just like the parent graph, but certain changes have been made. It's been moved left 3 units, and it's been moved down 4 units. And that's where the tip of the V is. So that HK value is sometimes called the vertex. It's kind of our starting point. It's going to be the point of the absolute value. Now from here, I can look at the A value. It's positive, so I'm going to be going up. But I'm not at my normal 1-to-1 ratio. I'm actually going up twice as fast. So I'd go over 1 and then up 2 for my next point, rather than my normal over 1 and up 1. I could go over 2 and then I'd go up 4. And I would get my V. In words, we could compare this. If we're asked to compare this to, say, the parent graph or what changes have been made, we can say that this graph is the same as the parent graph, but it's been moved left 3, down 4, and then it's going up twice as fast. So another example. Let's see, let's have negative 1/2 the absolute value of x minus 1 plus 2. So again, just looking at the equation, I know that this is an absolute value graph. It's going to be a V. It's been moved right 1 unit. It's been moved up 2 units. And then it's opening downward because the sign is negative. And it's going to be fatter than normal because it's a 1/2. So if I want to sketch this graph, I always look for that vertex. So I've moved right 1, I've been moved up 2. So there's where I'm starting. I'm now going downwards, but at half the normal rate. So if I go over 1, I'm not going to go down 1, I'm only going to go down a half. If I go over 1, I'm only going to go down a half. So I'm going to end up with a much fatter downward opening absolute value. Again, in words, if we wanted to compare it to this, we could say that it's been moved right 1, it's been moved up 2, it's opening downward, and it goes down at half the rate that it normally does. So this enables us to actually graph absolute values relatively quickly as a sketch, or at the very least to be able to compare them to the parent graph.